I am Rahul Patel. I work at Flownex as an engineer, and we develop a software called Flownex. The software is a 1D simulation software that solves heat transfer, that solves the fundamental physics of flow and heat transfer of components in large thermal fluid networks. It is also a 1D approach that means that it's quickly and very efficiently when it comes to solving systems. And when we mention systems, it can go from as small as one component to large systems, where CFDs take really long time to solve in terms of flow and heat transfer. So Flownex works on a system level based, meaning that it contains a large library of components that are widely used in the industry. We also have some advanced fluid models, consist of two-phase flow, compressed fluids, mixtures of mixtures, solids, and we also have a library for the NASA CAE combustion library. Linux can also solve in steady state and transient simulations, both being very efficient and quickly as well. We also have control library that works pretty well with the transient analysis, where you'll be able to control some of your components in order to maintain certain conditions in your system as well. Along with that, you'll be able to integrate Flownex with a third-party software, meaning that you can couple Flownex with a lot of other third-party softwares widely known as the ANSYS, MATLAB, Excel, and you can name the rest as well. Regarding the quality of the software, Flownex is developed with an NQA1 and ISO 9001 environment, and that ensures that we meet the best standard of quality compliances in the industry as well. We do release our softwares are released that are tested under nuclear verification and validation. It means that it goes through a very strong verification and validation procedure in order for us to make any release of the software as well. Regarding the software itself, the interface is very user friendly. We have a help manual as well for every component that exists in Flownex, and every feature or every tool that exists in Flownex, there's a help manual that can assist you and guide you on how to use that component or that feature in Flownex as well. Along with that, we have a dedicated user support, meaning that if you're struggling with anything or you have a question regarding Flownex or you need assistance with any type of simulation, you can contact us at support@flownex.com and our support team will get back to us at their earliest convenience. These are some of the clients that we have for Flownex. This wouldn't be all, but this is one of the clients, some of the clients that we have that are really big in the industry as well. Some are South African, some are international for us as well. One of the biggest one, we have Rolls-Royce, we have Solar Turbines, General Electric, and many more to name as well. Then regarding the water distribution, I'll start with simple examples that we have in Flownex, going towards complex examples. So talking about water distribution, it's more like transferring a fluid from one point to the other point. That includes pump sizing as well. So you'll be pumping fluid as well. So you can do pump sizing in Flownex, where you'll just require a simple geometry of your pipeline and pumps. Then you can use that in order to size your pump and get an actual pump from an OEM and obtain a pump curve from the OEM. So to do the pump sizing, you'll use a component called the basic centrifugal pump in Flownex, which is the best suited pump for pump sizing in Flownex. And using that, you can get a good view on how you'd be sizing a pump or what type of pump you'll need in order to pump this much water along this long pipeline as well. Then we'll also have flow balancing. For example, we'll be working with a sprinkler system where we need equal flow rate in all the sprinklers, but they're at different elevation or different pipeline sizes as well. So you can do designing in Flownex, where you can design the size of the valves as well. As you can see in the picture below, it's an animation that that is used in Flownex that will change the valve diameters in order to obtain 75 kilograms per second in each pipeline as well. So this will be the designing in Flownex. It uses the designer setup. There's the feature that's available in Flownex. So you can use that specific feature in order to design the valve sizes to obtain the desired mass flow rate. Then most of the water distribution system, they are done over elevation, or they have height difference. So we have head, and that means that there will be somewhere in the system where water hammer will be generated if a pump shuts down or a valve suddenly closes. Then we'll experience a water hammer. So water hammer simply means that it is caused due to the water coming back, which causes pressure spikes in the pipeline that can burst the pipelines, causing a massive problem in the system itself. So to avoid that, you can simulate water hammers in Flownex as well, and you will be able to predict what's the highest pressure that you might experience in the system and how you can mitigate the pressure spikes in the system. So in this scenario, you will see we have a pipeline system where we have a valve in between. Then the valve suddenly closes. So it's a transient simulation where the valve will suddenly close, and you'll see that we'll have pressure spikes that can go up to 2.4 thousand as well, more than 2.4 thousand. Then how to mitigate the system in Flownex and how to see that if your mitigation system really works. So we have put an accumulator just before the valve. So if the valve starts if there's a sudden close on the valve, you'll see that the accumulator will mitigate all the pressure spikes, and now our maximum pressure will be less than 1.5 thousand. So you can do water hammer simulations in Flownex as well. Then we have pressure drop calculations, where we have a very long pipeline where we're pumping water from the bottom of a pond or something, the bottom of a hill. We are pumping it to the top of the hill, and we'll notice the pressure drop in each and every pipe that will be in the pipeline on how's the pressure drop going as well. So the graph shows the pressure drop along the pipeline in the system as well. So you can also simulate pressure drops for very big pipeline systems as well, where we require those pressure drops in the water distribution systems as well in order to know what's the pressure at the outlet of every water distribution system as well. Then we have some slurry networks. It's not related to water, but slurry networks do contain water, so we'll need water to move most of the particles as well. So that's where slurry will also be part of this water distribution system in some sense, where we'll have to provide water to the particles, and you can move that as one as well. So you will be able to do slurry simulations in Flownex as well. The interest of point will be slurry pumps and slurry pipelines, and you can do hydraulic transport of slurring slurry, typically 5% to 30% of concentration by volume as well. You can also simulate non-Newtonian flow. I know this is out of the presentation where we have slurries, but we'll be discussing about water distribution. But this also plays a big role if we had to talk about water distribution networks as well, in that sense. Then there's just more on the slurry on how we would be graphing all those particles with respect to water, and how we can model that in Flownex as well. This is one of the nice examples. We have a chilled water reticulation system as well. It's more of recycling the water in the system as well, where we would be distributing it around two pumps and using valves to control the flow through the pumps as well. So the area of point will be vapor compression cycle and cooling towers, bulk air coolers, water circulation piping, and pumps as well. So this is where the Flownex capabilities play a big role in it, where we'll be able to use PID controllers to control the valve opening in order to make sure we have a certain flow rate that we're looking for through the pumps or through the pipes as well. So you can incorporate pump curves performance by importing individual performances and efficiency charts for each pump. This charts, we can get them from the OEM, and you can load them in Flownex as well. You're not limited to the charts that are already in Flownex, so you'll be able to load your own performance and efficiency charts for each pump in Flownex in order for you to model your system as accurate as possible in order to obtain efficient results as well. Then you can also incorporate the performance of cooling towers, bulk air coolers by importing the heat transfer characteristics of each as well. It's the same like pumps. You will get a chart, then you can just bring it to Flownex. This helps a lot with the results that you obtain in order for us to simulate a very accurate model in Flownex as well. You can also simulate the effect of ambient conditions and hot mine water temperatures on chilled water temperatures. That means that now you'll be able to also play around with temperatures to see that the water that you're busy distributing or recirculating, how will it get affected? Will it change its phase or not as well? So you will have the control and analogy as well in Flownex as well that you can use to control the water the water that is being distributed along the pipeline through valves or orifices or pumps as well. So we have pumps that use variable speed pumps where you are able to change the speed of the pump as well using a controller based on the flow that you're looking for as well. While I'm still going, if you guys have any questions, we can also reserve them for later, or you can also stop me and ask me in between as well. That will also be great for us. Then we have some vapor compression cycle. This is more on the two-phase side, where we have water in the vapor form, and we're trying to circulate that vapor in order to distribute it around other subsidiary systems. For example, we would use a ranking cycle or just a compression cycle as this one, where we're just using water to heat up some other systems as well. So we are distributing water to heat up subsidiary systems in the cycle itself. So area of point would be compressor, condenser. We have some expansion valves, evaporators as well. So the Flownex capabilities will be incorporating compressor performance by importing individual performance and efficiency charts for each compressor as well. So either from the manufacturer or the measurements that we'll get, you'll also be able to model control mechanism of the compressors and expansion valves in single dynamic vapor compression cycles as well, using the Flownex capabilities as well. Then you can also do calculations of heat transfer that is due to the internal or external tube fouling. So this is just an example that is used to explain that you can also do heat transfer in the water distribution systems to make sure that the water that you're distributing is not losing heat or is not gaining heat, because sometimes we'll be distributing water over long pipelines. And then we will have to make sure that the moment the water reaches the end point, it's not too hot or it's not too cold due to weather conditions. So you can use Flownex to get a rough idea on what will be the water temperature at the end. And using that, you would know if you need to insulate your pipe even more or the insulation is not working at all. So we can use that. We can use Flownex to get those results that we'll be looking for in that sense. Then we have some compression cycles. So this is also on the pressure drop side of the system. So it's just an example used to explain the pressure drop as well, more in the water distribution systems, where you can use the compression cycle, where you can compress the vapor, because water is incompressible. So you'll change it to vapor, then you'll compress it and you'll transfer that vapor through large pipeline systems. And at the end, you can use condensers to condense the vapor back to liquid. And that's how you use the water again on the other side as well. So you'll need to design your cooling water pumps as well, since we will be dealing with vapor, meaning that we'll have high temperatures and high pressures as well. So we'll have to design water pumps that can cool the vapor as well, condensers that can do the variation in the condenser, which will take in consideration the level of the condenser, the pressure that it can take, the maximum temperatures we can go in the condenser as well. So you can do all this design in Flownex as well, using the software. and you'll use the inbuilt components. There's no any intense components that you'll have to bring to Flownex. There's already inbuilt components in Flownex that makes it very user friendly for anyone who's planning to use Flownex as well, because all this calculation is done in the background of Flownex. So you'll be able to calculate what's the effect of condenser pressures due to the vapor leak in the system, or we'll have the levels changing in the condenser, how that affect the pumping requirements, how the operating condition or the cooling water temperatures fluctuating on will affect the cooling performance in the vapor compression cycle as well. And then we have a water reticulation system as well. The area of interest mostly will be the pipe network, or we'll have water storage dams as well. We'll have pumps, we'll have turbines, we'll have spot coolers as well. So those the capabilities will be you can simulate the water distribution in a complex pipe network in Flownex itself. So this is one of the example where we had a water reticulation system in South Africa for one of the company. Where we modeled the entire system for them in Flownex and showed them where they will experience pressure drop, where they will experience less flow, or they'll have high velocities in the pipeline. So we managed to get all those in Flownex as well. And we also managed to make a human interface in Flownex. So the image that you see on the right top right, it's a human interface image, which is very easy to um, use in presentation and show to people on how you'd be able to see your network as well. So normally in Flownex, we'll have pipelines, we'll have valves and all those things, which gets very complicated to use in presentation. So you can create your own human machine interface, HMI, in Flownex itself that will make it much easier for one to present it to the client or the end user at the end as well. So you can model complex piping network in Flownex as well, that uh, where you'll be distributing water over a very large system, for example, from dams to residential area. Then you would want to know where you will experience more pressure drop, how the elevation really affect the pressure in the pipeline as well, where you can experience water hammer as well, where you can put valves, or you will need pumps as well in order for you to increase the pressure of the flow as well in to meet the water the mass flow requirements at the end as well. So Flownex becomes a very perfect tool when doing water simulations, water reticulation or water distribution simulations as well, because you can incorporate all this terminology in your network, and you'll be able to follow them through very easily as well. So you can also simulate stuff like pressure rise caused by loss of load on power generation turbines. For example, you're using generation turbines to generate electricity while distribution water as well. So you can also simulate that. You can also simulate the pipe wall heat transfer, as I mentioned earlier. So it's just in the water distribution, you also want to know how much heat you're losing or how much heat you're gaining throughout the entire system in order to maintain a certain temperature for the end user as well, in that sense. Then we'll have like ventilation fans. This is more on the distribution of the air side as well. So we can also do distribution of air in pipelines as well. That's more on the air side more than the water side, but they have more or less the same terminology, where you will have different flow requirements, or yeah, you will have different flow requirements at each end. For example, some rooms will need more cooling, some rooms will need less cooling. You can do that in Flownex as well. And you can see on the top right, there's a pipe network that we have out there. So we can use the air network to explain the water distribution. We can have a simple pipe network, just the one that's on the top right, where we moving water from one end to the rest of the ends, where we have different requirements of the flow. And you can do that in Flownex as well using the design features inbuilt in Flownex, or you can also use the boundary conditions to see what pressure you will need, or what's the pressure rise or what's the pressure drop you will require in order to meet those conditions as well. I'm gonna use one of the case studies we have. So this is a residential water distribution network that we did for a client. Uh, I can't share the network because it is under the IP, but what I can do is share the overview of what happened. But you can request for a network and we'll try to simulate a simple example for you and we can just share it with you as well. So the current challenge that was existing was an existing water distribution network for a village needed to be expanded. So we need to increase the water distribution network for a village to include a new block of houses. So they were building a new residential settlement next to the one that exists, and it required an expansion of the water distribution network in the place as well. So the expansion create a high demand of the existing infrastructure, and we needed to ensure that the water pressures are delivered at each house. So this is where the challenge comes that we have to meet the required water flow rate at each house in the settlement, and we have to make sure that there's enough pressure in the system in order to maintain same pressure throughout all the new settlement as well. The current the village that's being expanded with new blocks of houses as well. The benefits we had with this was the entire grid could easily be simulated and we could ensure high fidelity and accurate results at each point of water delivery, meaning at each house. And that was the benefit that we had, that we could also see was the pressure and was the flow rate that we're getting at each point of water delivery. The effect of the entire system could be seen and correct measures could be taken to ensure adequate delivery as well. And we could also simulate the seasonal change variations in the consumption of water. So, for example, in winter, we'll have uh, more hot water consumption, so we have to deliver more water on that side. Or in summer, we'll have people watering the garden as well, so we have to maintain the same water pressure and in every season. So we could simulate that as well in Flownex, and we could also evaluate what's the effect of more consumption on the existing water system that we have as well. So this was the solution that we had. On the right hand side, you will see there is block A. Then the new residential area that was being created was block B with all the new houses. And we need to make sure that we could supply water to block B as well, making sure that we're maintaining the same water pressure and flow rate in block A as well. So the entire distribution grid was built and simulated in Flownex, where we use the existing data and we use that to build the entire network in Flownex. That and building the entire network in Flownex allowed us to investigate thoroughly and test various conditions after the expansion of the current reticulation system. So we integrated the water distribution for Block B as well, and with the integration, we could investigate a lot of test cases in Flownex itself, where we would try and see that what would happen if we have more consumption in block E, what will happen block B, what will happen to block A. Will the water start decreasing, the pressure of water will start decreasing, or we'll have less flow in block A. So we could test all those cases in Flownex. Then we use the optimization and design capabilities of Flownex in order to design the system and maintain adequate water pressures during peak demand as well. So we'll notice that some time of the day we'll need more water, for example, in the morning and at night, where people will go to work and they'll need to bath or shower, then we'll know that the water demand will increase. Then we had to make sure that we meet those water demands, and you could do those simulations in Flownex as well to see that we'll meet the water demands or not. Then the objective of the simulation was to model a steady state operation of the current water reticulation system. So there were transient simulations not done in this case. We just were looking forward to the steady state simulations. Then the additional houses must be added, and the size of the connecting pipes between the blocks were investigated as well in order to maintain water pressures of at least 2.5 bar at each home. So during the steady state simulations, we tried to optimize the system as much as we could in order for us to meet 2.5 bar at each house, including the new houses that were built, meaning that every house in block A and block B need to at least have a pressure of 2.5 bar. And we could do that simulation in Flownex to investigate will it really be possible with the um, current conditions, or the current reservoir will it be maintained, will it be able to maintain the 2.5 bar at each house. So this was the Flownex model, as you can see. So we have block A, then we also have block B. Then you'll see that at the bottom of the picture, we have modeled the reservoir through a pressure and a pipeline. Then this is how we could model the entire water distribution system in the settlement itself. So you'll see there's a lot of pipes, there's a lot of junctions as well. So all this thing could be modeled in Flownex, and you could identify your pressure drops, you could identify your flow rates, you could identify where you need pressures as well. And based on that, you'd make changes to the network or the pipeline as well in order to meet the pressures that you're looking for and the flow rates that you're looking for using Flownex. All this distribution could be done in Flownex, and it was a steady state simulation, so it was really quick and it was very easy for us to do any fault finding or root cause analysis on the network as well, to see where we can improve the pipeline system in order to meet the required flow rate and the pressures that we're looking for as well. So you'd be able to see that the conclusion that we could draw from this was the steady state simulation of the water reticulation system of a village was demonstrated in this example. As I mentioned, that a new addition of a block was done to the settlement, and we had to maintain a certain pressure that we're looking for. And to ensure that all houses have the adequate pressure, water pressure during peak demand as well, so we had to maintain that 2.5 bar. We noticed that we could do that by connecting a pipe of 0.15 diameter as well. So that this is where I mentioned that we noticed that using the same pipeline system, we noticed that we're not getting the same pressure drop that, I mean, the same 2.5 bar pressure at every house. So we tried to optimize the system, and we found out that having a 0.15 meter diameter pipes will make sure that we meet the pressure demands in every household as well. So this was just a simple example. There's various example on the Flownex website itself and case study forms where you can request for the networks, and we'll assist you with creating the networks as simple as possible for you to understand how to simulate a water distribution system in Flownex as well. I think that will conclude my presentation.